video. What is the noise in double sideband suppressed carrier AM wave? What is the noise actually? Okay. Now, for that, we need to know about a practical communication system model. Practical communication system model. Hope this picture doesn't look to be new for you, right? Is it something very new? As in, right? Is it new picture? Now tell me, what is this? This is an AM double sideband suppressed carrier. I think most of you know only about this guy. See here. This is the normal communication system module. You have a message signal m of t with a maximum frequency of omega m. Then it is modulated using double sideband suppressed carrier modulation technique with a carrier frequency omega c. You will know about it. Then the signal is transmitted. How does the modulation is done? Can you see this figure? Do you know this? Once upon a time, long ago, in the same class, same semester, I have told you about this. Yes or no? Right? You know, your message signal multiplied by carrier signal, you get double sideband suppressed carrier wave. Many times I have done it on the board. You people have counted it also. I know. Right? Then you will definitely know about it. Okay. Let us everybody know about it. This is what transmitted. Your signal is transmitted. Fine. Signal is transmitted. Now what is ST? ST is the signal. This is what the power of a signal transmitted, or you can say transmitted signal power. Right? So then, while communicating through communication channel, there comes noise. One you cannot avoid it. Right? This noise is getting added to the transmitted signal. Right? Okay, fine. Now, what is received at the receiver? This is the receiver part. If you see this, okay. If you see this, what happens? This is your transmitter, yes or no? This is your transmitter. What is this? Tell me. Come on, you should tell me the answer. You are more expert than me now. And what will be this part? This is the receiver. Now, this is the passband signal. The passband signal, right? When you receive the signal, because of this noise, it has all the frequency component. Yes or no? Yes or no?
Yes.
What is required out of that? Only that band of frequencies omega c minus omega m to omega c plus omega m. Yes or no? Only that band of frequency is required for you. Right? What do you do in that case? You use band pass filter. And while doing band pass filter, the noise also will convert into pass band noise. That's what I have done in your video one. Your noise will be converted to pass band noise. Pass band noise. The spectrum of the noise, which was like this, flat throughout minus infinity to plus infinity, now will become pass band noise. right? So now, if you see at this point, you get signal plus pass band or band pass noise. Understood? Can you tell me what is this process? Do you remember this somewhere? You have studied this. What type of detection is that? Synchronous detection. Yes or no? Demonstration of double statement suppressed carrier wave by a technique called as synchronous detection. What do? You multiply the same modulated signal with the same carrier, and then you use a low pass filter with a cutoff frequency omega m. You will get back the signal. We have done this earlier. We have done this earlier. Right? Right. We have done this earlier. Definitely. No doubt about it. Now, what next? This is explained now. What next? We need to know once again signal power at the input of the demodulator, noise power at the input of the demodulator, and signal power at the output of the demodulator, noise power at the output of the demodulator. All those things we need to calculate now. Then find out signal to noise ratio at the output here. Right? That's what we're going to do now. See here. Can you tell me if m of t is your signal and AC cos omega ct is your carrier, what will be the output you get at this point? Come on. If this is m of t and this is AC cos omega ct, what will get here? So that is your DSBSC wave. Come on. That's your DSBSC wave. See. Now tell me what will you get as a yi of t? Signal plus which noise? Wideband noise. Signal plus wideband noise. Okay. Next. What do we get at the output of the bandpass filter? Signal plus bandpass. And what you get here, right? Multiplication. Yes or no? This multiplied by cos omega ct. Right? Okay. This multiplied by cos omega ct. I will remove all this thing. I'll remove all these things. Okay. What you will get here is signal plus pass band noise. What you get here is this multiplied by cos omega ct. And what you get here is the low pass filter. Write it as it is. Okay. Low pass filter version of this multiplication. You have that much equations with you. Right. You have that much equation with you. Now, what you are interested is signal power at the input of the demodulator, noise power at the input of the demodulator, signal power at the output of the demodulator, noise power at the output of the demodulator. These things we will have to get it from these equations. Right? Okay. Now let us do one by one. Okay. To do this, do we need the entire communication system model? No. We need only receiver, right? So I'm just redrawing only the receiver here. See here. Only the receiver. We are interested around these parameters. You know what is the equation at this point, right? At this point is the equation. Okay. Now similarly, what is the equation at this point? You know it, right? Fine. I have no slide for input. Yeah, here. Right? I need only receiver side. I don't want transmitter side to do noise analysis. I'm interested on signal, input signal power, input noise power, output signal power, output noise power. Now, the equation at this point is this one. Yes or no? Right? I will redraw this equation. I will rewrite this equation. The equation at this point where I have to find out what is signal power and what is. Now look at the equation. It is quite clear, crystal clear that which is signal component, which is noise component. Yes or no? Right? Which is signal component in this? This is signal component. Now this is noise component. It's clear. Now you just have to find out root mean square value, power in that's all. Right? So now you can find out the root mean square value of this. It is coming to be this one. Right? Okay, because AC cos omega CT, okay, AC cos omega CT will give you value AC square by 2, root mean square value. Right? Of course. M square. Basically, okay, it's M square. Okay? It will be always there. Okay. Then, anything else? That's all. And this is going to be your, yes, I have understood now. Okay, now next. Noise power. Noise power. Hope you remember, we have already done this in baseband. Right? Listen carefully. Noise power is equal to root mean square value of the noise NOT. Right? Now, just look at this. Just look at this. Can you tell me what is this? Tell me. Can you tell me what is this? What is this? Power spectral density of a pass band or band pass. Right. Now, root mean square value is nothing but the area under this curve. Area under this curve. Right. So, area under this curve is 2 times. I'm taking 2 times. Okay. 2 times FC minus FM to FC plus FM. FC minus FM to FC plus FM. This is Sn of F. This is power spectral density into dF. Now, what is this actually? This is theta by 2. Theta by 2. Okay. Now, substitute that. Okay. Substitute that. Remove this for time being. Substitute this. What you get? Root mean square value. 2 into theta into Fm. Right. I have already explained this in my previous video, second video. Okay. So you get Ni as input noise power as 2 into theta into Fm. Understood this? It's okay. What you got now? Tell me. SI and Ni. Right. Now, can you compare this with the SI and Ni of your baseband system? You can do, right? Compare that. Right? You can compare this. I have not done this. You already know. You already have that SI by Ni for baseband system with you. You compare it with this. Fine. That's why I want you to watch the video. Okay. Fine. Next. What next now? What I should do next? Output signal power and output noise power. How do you calculate output signal power and output noise power? Now tell me. You proceed yourself now. You require equation at this point, right? You require equation at this point, right? How did you calculate SI and NI? From this equation, right? So how will you calculate SO and NO? From this equation. From this equation. In this equation, you have to. In this equation, you will have to find out what is the signal component and the noise component. Right? What is the signal component and the noise component? So you're going to use this equation. Right? In this equation, you find out what the signal component and noise component. This is very easy for you. Right? Okay? Now, from here onwards, you are going to understand. See here. You have this equation here, right? What is the difference between this equation and this equation? What is the difference between this equation and this equation? It is just low pass filter. So you need to see through the frequency components of the term inside the low pass filter term. See which are all the components will be stopped, cancelled by low pass filter, and see which are the components passed with the low pass filter. And I told you that this low pass filter cutoff frequency is omega m. What is the meaning of that? If I say only what will be passed? That is what is that actually? What is that? Message signal. Only message signal will be passed. Your carrier omega c to omega c will not pass at all. Right? Now, this is what the equation you have. Now, what is n of t? N of t, already you have the equation, right? What is that? You have n of t equation written in terms of its in-phase component and quadrature phase component. You have both. Substitute that. This n of t, you substitute in-phase component and out of quadrature phase component, you get this equation. Yes or no? Look at the equation. This part you get by substituting n of t, this is your n of t. This is your n of t. Fine. Okay. Now, can you just solve this? You are expert in mathematics. Solve this. Solve this one. Okay. Multiply first. This will become cos square omega ct. This will become once again cos square omega ct. This will become ns of t sin omega ct into cos omega ct. Trigonometry. Right? Cos square theta is equal to 1 plus cos square theta divided by 2. So you get this. You get this. Now can you tell me in this which are the components will be passed through low pass filter and which are the components are not passed through low pass filter? Tell me first whether this will be passed. Yes, this is pass. This will be, this is fail. This will be pass. This will be fail. This will be fail. Now, what is the output, final output now? Final output will be AC by M of t plus NC of t by 2. Right? Yes or no? Come on. Right? Now, in this, tell me which is signal component and this noise component. Definitely, this is going to be signal component. Okay, what is the this is going to be, you can calculate S naught from here, right? Root mean square value. So S naught is a root mean square value. You get this. You get this. Now, can you compare it with SI? It is SI by 2, right? Less than BPT. Understood. Now, how do you calculate root mean square value of NC of T? My second video, first video. There I told you that your root mean square value of quadrature, that is simplest component, that's n square, it is equal to n, this is n square, okay? Same, these are same. I told you that. Right? So in that case, you can write, see, this is, you know about what is n square of t. This we calculated, right? Just now, root mean square of n of t, right? We substitute that. 1 by 4, 2 times theta fm. That will give you n naught as 1 by 2 theta into fm. What is the next very important parameter to calculate? Signal to noise ratio. Signal to noise ratio. Substitute that. I'm substituting in terms of SI. Why I'm substituting in terms of SI? I want to compare it with the baseband. In baseband, you got signal to noise ratio as SI divided by theta into FM. Yes or no? Right? That's why I'm doing it. That's why I'm doing it as SI by 2 divided by half into theta into FM. So this gets cancelled. Ultimately, what you get? SI by theta FM. That is equal to gamma. Comparison. Now, see here. Is there a difference between baseband system and passband system? The noise effect, double sideband, suppressed carrier AMI is same as something you transmit without modulation. By 16. Right? I am a very weak person. Right? I am wearing some brownies will actually kill me. Right? For that, I will take some, bouncers. Right? So first I will make baseband system. Those rowdies will, they will attack me. Right? I have some effect. Yes. Right? Now I will go with the bouncers. Even though I will go with the bouncer, also same effect. Whatever attack I want to attack is maximum. It is something like this. The effect of noise on the baseband system is, it is gamma only. After modulation, after you just make it very strong by using high frequency carrier, noise effect is same, gamma. It doesn't change at all. No use of bouncers, right? So why we are using this for comparison purpose? It doesn't mean that you can transmit baseband signal as it is. It's not possible, you know that. What's the reason for that? You need to add carrier and then only it can go, right? Okay. But noise effect is same. I understood this. Now this is the noise effect for which type of modulation? Double sideband, suppressed carrier, AMP. What about AMP? What about AMP? Right. AMP is different from double sideband suppressed carrier, right? So don't you think we need to do that also? Right? Tomorrow's class I'm going to do it. Right? What about FM? FM is something we need to know. What is the effect of noise? We will compare it with the baseband system once again. We'll see whether it is equal, whether it is half of that, whether it is 2 times. We'll see all those things. Right? That's what I have put in our entire data. Right? Okay. So we have 2 more class left, right? 1 more class left in this one. Right? Okay. Mobile okay. Kevin, Sharon,
Yes, sir.
Jahan James, Jahan James. So, Donald is not there. Yes. No. Unless it's there. Donald is actually.
Yes, sir.
Where I'm thinking not there. Now we are calling Akash Ghosh. Yes. Atul. Dhruv Sharma.
Yes, sir.
Parth. Sandeep.
Yes, sir.
Aditya.
Yes, sir.
Anjali Singh.
Yes, sir.
Adili. Yes, sir. Deep
Yes, sir.
Rahul Singh. Okay, so we will meet next class. So I will share the video of this, okay?